Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss some of these advanced processes, and we specifically try to focus on one of the top down process that we have told the name as ball milling or mechanical alloying. So, mechanical alloying in this particular case, the term itself says that it has something to do with the alloying of different elements. Means I can have copper, I can have nickel, individual particles, and by this mechanical alloying technique we can make a alloy of nickel and copper. However, using the same device, means inside a vial we put these two different composition of two different particles. We can also put a single composition larger size particle and we can make size reduction. In that case we call it as ball milling. Okay. So, here balls as a assist for those crushing or it impact on the particles, and it basically refine the size of those particles. So, in a top down process using this mechanical alloying technique, where the particles are milled using some high energy ball mill. So, the ball mill consists of a rotating disc where some vials or a container is placed, and the initial powders with a larger size are placed in those vials. Here we also take assistance of some hardened steel or tungsten carbide balls. So, here these are the balls and these are the initial powder particles. Okay. So, I can think about two different color of two different component. As I said, let us say nickel copper, or let us say aluminum or copper or whatever as you prefer. Now, this process itself has many different parameters to control. However, the grinding medium here, like the balls that could be made out of a steel, or let us say we can also use some ceramic balls. Okay. It depends on which material you are going to produce from the initial material. Okay. So, let us go through this process. The process creates actually heavily deformed mechanically alloyed particles with nanoscale internal structures, and these particles are subsequently compacted and sintered in order to make the final product. So, ball milling or mechanical alloying produces very fine size particles which later on need a secondary process as compaction or consolidation in order to make a bulk scale nanostructure by those technique I said, like a pressure induced sintering and so on. Now, a typical attribute of this mechanical alloying process is that we can produce a very fine dispersion of this solid phase. Let us say we can also go for some oxide particles, and let us say the oxide particles that are mixed with some alloyed particles. Okay. So, here this is like a physical mixing. Okay. So, oxide is embedded in a metallic alloyed powders. On the other hand, we can also get extension of the solid solubility. Means what I am talking about, that if I take a simple binary phase diagram, okay, here this is alpha and this is beta. So, in that case actually the extension maximum solid solubility of B in A is here up to here. So, the extension of solid solubility can be done. So, I can produce the same alpha phase, okay, where which is become more B rich than the A. Okay. So, then the conventional equilibrium process alpha. So, that is possible. We will discuss the thermodynamics of it later on. However, let us try to go through what are the other attributes of it. So, let us say we can definitely refine the grain sizes down to the nanometer range. On the other hand, we can synthesize novel crystalline or quasi crystalline phases, okay, or we can also produce some amorphous phases, okay, and disordered intermetallics. By keep on putting high energy in a ordered metallic intermetallic, we can produce some disordered of ordered intermetallic, or in some cases where alloying is not possible in the liquid state. I may have a component of A and B and that does not mix in the liquid state. So, I can simply take A and B in the solid state and put it inside in a mechanical alloying device and then we can alloy those powders. And inducement of the chemical or displacement reactions at a low temperature. So, means during milling itself some mechanochemical synthesis can be done. On the other hand, it is a scalable process, means we can go for an industrial scale in order to make a very large scale. So, here this is a typical schematic is shown here, that if we repetitively heat let us say two different such kind of composition and then it is heated by two of these balls, like such a ball, very hard balls, then we deform the structures and these both of these particle can be welded together and there will be some diffusion and it will be alloyed because the surface atom keep on increases. So, the solubility limit also increases. So, we will go into detail of those things in the next slides. Now, this typical mechanical alloying process it was discovered while processing of oxide dispersion strengthened nickel based superalloys for gas turbine application in 1966. So, this is not a very old technique. So, in that case actually people think about such kind of introduction of very high energy using some planetary motion. So, here you see that this is a vial where we place those initial powders and the media some very hard spheres of stainless steel or hardened steel or tungsten carbide, and they basically rotate the vials rotate along this direction. Okay. On the other hand, in its axis, on the other hand the whole vial on a bigger disc it rotate along this direction. So, this is like a simple planetary motion. So, we call it as a planetary ball mill. Okay. So, both the centrifuge force that work along this direction and there is a movement of the supporting disc. So, it basically goes into such a way and we can get this powder particle that crushed by heating that medium during the rotation of the grinding bowl. So, in that particular milling process we have many different parameters that can control and to optimize the process parameter. So, here it depends on what are the mill we choose. So, there may be a planetary type of motion in a mill, we call it as planetary ball mill, or maybe it can be a vibrator type of mill or it could be a attrition type of mill. We will discuss what are those mills name means and how the process goes on. However, this container means I am talking about the vial that could be made of hardened steel, tungsten carbide or maybe some ceramic. Okay. However, one should prefer that the grinding medium as well as the vial should be made of the same material, that will increases the efficiency also. Now, this milling speed or energy can also be controlled and milling time can also be controlled. I will show you later on what is the effect of milling time and milling speed. The energy input into the system depends on these parameters actually. So, the type, size and size distribution of such grinding medium or balls is also important. So, this is a typical image of a vial. Okay. So, like a bowl, inside we pour these balls and the powder particles. Now, another important aspect, that the ball, that is the grinding media, and the powder that we want to mechanically alloy or simply size reduction want to make, the weight ratio is also important. Now, the extent of vial filling, milling atmosphere, this could be done in a inert atmosphere or some different temperature. So, we can also make some cryogenic temperature milling, that is called cryo milling. Now, there are some process controlling agent, okay, if there is some sort of reaction goes on here and also the temperature, these are some of the very important aspect of a mechanical alloying processes. Now, the two other mill that I told about, that is a attreation mill and a tumbler mill, and these are typical different types of high energy mill that are adopted for some industry purpose and for pilot scale production process. So, here you see these are some rotating pillar here that rotate in a grinding medium, that is the balls are present here, and this is a stationary tank, and this is rotated using a drive shaft, and this is a typical attreation mill. Whereas, in case of a tumbler mill, actually the inside a jar we place those balls and those balls goes up and then it basically falls down. So, the rotation speed should be chosen in such a way, so that all the balls should not be centrifuged. So, the balls will go up and then it should fall and make impact on the bottom balls, including those powder particle that has to be mechanically alloyed or the size to be reduced. That is very much important. So, the speed, it means that we cannot choose any speed. If the speed is too less, then the ball will go maximum up to such a height and then it will again fall here. If the speed is too high, all the balls will be centrifuged. So, a optimum speed has to be chosen, so that the ball can go up to higher distance or higher height, and then it will fall, so that it will cause impact. And these are some of the very important parameters, or let us say the milling parameters that should be chosen. So, these are simple drive roll which basically assist the jar to move, and an atreal mill actually was the very first. In this case, it was one of the very high energy ball mill that is used for this mechanical alloying purpose, and the atreal has a vertical cylindrical tank, and which the powder and balls are charged, and the movement of these balls and powder is achieved by horizontal impellers. So, these are the impellers here, and which is attached to a vertical shaft and which is made to rotate, and these impellers energize the ball to cause a size reduction of the powders. So, this basically assists the ball not to segregate, but the ball has to rotate along this way, so that they cause impact with each other, and when the powder particle comes in between two balls, then the particle will be alloyed, or let us say the size will be reduced. So, both will causes. So, higher capacity of these atreal mill are often used for the industry. In case of a tumbler mill, this is also used for mechanical alloying purpose, and if the initial particle size is sufficiently large, the balls are pinned in the inner wall, and the mill, because of the centrifugal force dominating over the centripetal force actually. So, this is a typical schematic of such a tumbler mill. Now, initially I have shown you one of the image of a planetary ball mill, where we causes a planetary motion of the vials. So, like the vial rotate in its own axis in the direction, and then in the opposite direction, in a clockwise direction, it rotate on a bigger wheel base. So, we get basically effect of both the motion. So, the initial the vial itself rotate in the counterclockwise direction and in the clockwise direction on its base. So, the movement of the supporting disc is also important in this case, and the centrifugal force is also very much important. Now, if you compare between these various types of mill, the comparison basically says that the ball velocity that could be very high in case of a planetary mill. So, you see this is like a velocity, whereas simple mixer mill or atrial mill cannot go up to such a case. However, for a smaller scale we can take assistance of this uni-ball mill. What is this causes? Sometimes giving higher energy to the system make the complex processes very worse. So, in that case a very low energy input when it is required, then uni-ball mill here it simply rotate and the ball actually goes to the next process and very small amount of energy can be given. However, we can place a magnet and move this magnet to upward side in order to control that the ball will go up to certain height and then it will fall. Okay. So, this is for let us say a higher energy milling mode. So, we can choose the mode by using some sort of magnetic action or with the interaction between the balls and the magnet. So, uni-ball mill actually consists of stainless steel horizontal cell with a hardened steel balls, and this movement of these balls are confined in a vertical plane of the cell wall, and it is controlled by a external magnetic field whose intensity and direction can be adjusted. So, this is a very slow process and also the energy input is relatively high. However, we can go for let us say a higher amount of the mass. The atrial mill is used for let us say the industry purpose where we can reach up to 100 kilogram. So, compared to a planetary motion we can scale up the process in a industry scale. So, all these processes can produce a very fine nanoscale structure or amorphous structures and so on, or let us say very bulk scale which can be consolidated to make a fine product. On the other hand, the disc on which the vial is mounted, it can be rotated in the opposite direction, and so that the vial it gives a centrifugal force to this case of a planetary ball mill. So, we have compared with various types of mechanical alloying devices, and all of them have their own benefit advantage depending on the ball velocity, the process parameter you choose in order to alter the energy input into the system. Now, if we look at the mechanism of the process that control this mechanical alloying, we must consider some of these systems. So, let us consider that I have a ductile system. Here I am not at all talking about the milling media as ductile. I am talking about the powder particle are ductile. So, I have two particle of two different chemistry which are let us say ductile in nature. So, what could be the sequence of operation that goes on? So, in that case the equiax ductile particle are flattened by some micro forging process resulting a flaky plate like particle. What I want to mean? I have two ductile particle that goes on these are the balls. Okay. So, this is just a curvature of that ball is shown here, and they goes between the balls, and when the ball causes impaction, then they are getting welded actually. Okay. And this causes some flaky shape of particles. Now, with increase the surface area of the particle, so initially I have some spherical particle. After welding of these two particle, let us say I have one particle which is like here. So, this is the one particle and it is welded together because it is a ductile system, and because of the surface area has increased during the impaction with the ball, it causes extensive cold welding with the powder components and further milling resulting sandwich like microstructure, which is a associated increase in the average particle size. So, if basically keep on welding things, then the particle size actually increases. Now, the particle size decreases because further fracturing of the particle that tend to become more equiaxed. Now, upon again further mechanical alloying or ball milling operation, these particles get fragmented. Okay. So, we again fragment this particle together. So, this this process is like a dynamic fracture or some sort of forging fracture type of process. Now, the number of the lamellar colonies of random orientation develop inside each of these composite particle. So, if there is two different component, I may get such kind of lamellar structure inside a particle, where I have two different chemistry of these particles actually, or composition of this particle, and the hardness and the particle size tend to reach to a saturation at the final stage, suggesting that these welding and fracturing frequencies need to be balanced. So, since the particle are ductile system, so there is a competition between the fracturing of the particles and the welding of these particles. So, these two process when it optimizes, then we can achieve a optimized condition or the frequencies of a particular particle size. So, this is one of the very important aspect. So, starting from a indirect scissor or let us say the welding, we have a fracture process, and both these welding process and fracturing process has to be optimized in some case. So, typical example for such kind of ductile system, I can choose nickel chromium, I can choose copper nickel, I can choose copper zinc, or let us say nickel aluminum system. Okay. So, here we will go for such kind of ductile system mechanism. However, the system mechanism may alter when we consider a ductile brittle system, means one of the initial particle is very hard and another one is relatively soft. In that case actually the ductile particle like nickel or aluminum, which is a FCC structure and very ductile, they are flattened and welded to each other during milling, whereas the brittle phase like zirconium, such as like it can be a oxide particle, they are fragmented and embedded in the layers of the ductile phase. So, let us say I have a flattened nickel and inside here I have a zirconium particle. So, this is a nickel and let us say this is a zirconium, or maybe it could be a oxide phase, okay, like TD nickel or like thoria disperse. So, this is like a thoria or an inside a nickel phase. So, they basically sandwich between two nickel layers, and as the milling proceeds, the layer of the ductile phase become coarsened and ultimately become unresolved, while the brittle phase is uniformly distributed in the fine particle of the matrix of this ductile phase. So, example of such kind of ductile brittle system like nickel zirconium or niobium, germanium and titanium diboride system. However, we may also have a brittle system, means both of them are very brittle. Okay. So, here we can think about silicon and germanium. So, we can mix these two intermetallic compound like nickel zirconium intermetallic and Ni11 zirconium 9 in order to produce a amorphous alloy. So, we can start with two different brittle phase and then we allow them to join together both in terms of alloying as well as the size reduction. So, both process can be chosen, and definitely the mechanism of such processes are also a little bit different. Now, as I said, the choice of a mill is also important, because each and every mills and their parameter control the net energy input. However, choice of the mill is very much essential in order to achieve your final product. Let us say a particular mill where I am talking about, let us say the planetary ball mill. Okay. So, where planetary motion is involved, and the atrial mill where I can produce a very high amount of yield of powders, okay, which can be possible in a industry scale. Now, which also considered a very high energy input. Now, in a planetary motion here, let us say I may start with a very fine powder, okay, and the fine powder reduction cannot go to a very high fineness. It is almost less. Let us say this is like a micrometer. I have started with 2 micrometer. Now, I can also start with 12 or 11 micrometer and keep on doing some milling. Here the x axis is the milling time and here is the mean particle diameter. So, the mean particle diameter keep on decreases, it reaches to something like 3 micrometer using a planetary mill, but taking the same powder and putting in a attrier mill, the size reduction can be much finer. So, it reaches to 2 micrometer particle size. And so, with increase of the milling time, only 4 hour of milling instead of 50 hour of milling using a attrier mill. So, we can reach to very final fineness. So, there is a benefit of each and every milling process. So, the time to reach is similar particle size during milling of let us say titanium diboride powder in a planetary ball mill or attrier mill. So, this was a titanium diboride powder that was chosen and the energy transfer is much higher in case of attriation mill. So, depending on the type of the powder, quantity of the powder and the final required particle size, a suitable mill can be chosen. So, this is just a case I have shown you with an suitable example. Now, the time is also very much important. So, how much time you will allow for a milling purpose. So, like a crystal size, here I am talking about maybe the particle itself is 1 micrometer, but inside a particle there are many crystals. So, those crystals size can be easily measured using X-ray diffraction and we call it not as a crystal, it is a crystallite size. So, means the individual domain that contribute to the diffraction. So, in that case that crystallite size can easily reach within let us say 100 hour from a 50 nanometer to 10 nanometer. So, in 2 different chemistry it shows a 2 different trend let us say. So, normally the time is chosen so that it achieve a steady state between the fracturing process and cold welding process. If we allow more and more time, then maybe it may get cold welded or maybe the fracture and it need to create some optimized situation. So, that these 2 process should be in a same frequency level. So, on the other hand I can also take let us say a germanium whose lattice parameter decreases, this is the lattice parameter of germanium and silicon, whereas my intention is to make an alloy out of it and then after alloying has begun let us say something like 5 hour and then the final lattice parameter is changing with time. So, as the alloying is caused. So, this is from a germanium silicon we are producing let us say silicon germanium during mechanical alloying. So, the parameters here are the type of the mill that we use, the ball to powder ratio and the temperature of milling. This could be also varied. So, the ball to powder ratio will simply allow to get a higher impact. Now, the milling time as I said is also important and the rotation speed that can also be controlled, because the whole centrifugal force can be controlled by the milling speed, because if I have such a mill and the speed it is rotating at a certain RPM. So, you can see here this is a titanium to aluminum niobium alloy powder. And let us say for 5 hour you can see some flaky shape of particles, right, some flaky shape of the particles. After 20 hour the size has been reduced, but the aspect ratio has not changed too much. However, if you go up to 40 hour you can reach to a spherical shape particles. So, this is one of the benefit. So, particle size in that case does not reduce below 15 micrometer, but the shape of the particle can be controlled with a suitable choice of the milling time. So, the change of the average particle size of the milling powder with the milling time is shown here, where if this shape is more preferred, then we have to definitely go through all these different mechanisms that play a crucial role. And now, as I said, the ball to powder ratio control the net energy input into the system. So, the ball to powder ratio hereby is very much important. So, I show you a plot here. This is a milling time versus particle size or grain size in nanometer, just a schematic. So, if you increase the ball to powder ratio, it is easier to go to a nanoscale. However, if you decrease ball to powder ratio, the size of the final particle size will be higher. So, the ratio of let us say this ball and the powder particle, the ratio means this is a ratio of the weight in terms of the weight of the ball by the weight of the particles or the powders. So, this powder to ball ratio or a ball to powder ratio sometimes referred as a change ratio or CR. So, it could be 1:1 to a 220:1. This is a very high ball to powder ratio actually. Usually 10:1 is a convention for using this kind of mechanical alloying purpose that are commonly used for let us say any planetary ball mill or specs mill, that is also a high energy ball mill. But when milling is conducted in a large capacity mill like Actrier mill or let us say higher ball to powder ratio, something like 50:1 or 100:1 is typically used in a larger scale. So that the probability of the impact with the particle and the powder particle as well as the milling medium, that is the balls, are increased. So, the higher the ball to powder ratio will basically shorten the time required for the whole mechanical alloying purpose, because we are putting more energy into the system. As an example, the amorphous phase can be achieved in a titanium aluminum system by a powder mixture in a specs mill. Let us say it will take 7 hours if you use 10:1, it will take 1 hour if you use 100:1. So, energy input is very high and you can achieve to the amorphous state within 1 hour of milling only. So, this is one of the very common example of let us say choice of the proper milling parameter. Now, besides all these processing parameter, one important aspect one has to keep in mind on processing these advanced materials using these non-equilibrium processes like mechanical alloying, that is basically the contamination. You are milling or we are milling in a medium using a vial and the ball. So, the vial and the ball, they may also add some contamination and change the purity level of the powders that you are going to produce. So, in that case, let us say a choice of proper vial and the media is also important. What I want to mean, let us say a mechanical alloying that has been carried out using stainless steel or let us say hard chrome steel, hardened steel, and a milling media is the ball and the container that can introduce a large amount of iron contamination in the powder. Let us say I take an example of I want to produce nickel aluminum intermetallic or some solid solution phases, and here if I use a stainless steel, then I do not contaminate too much, but if I use a tungsten carbide vial and ball, then I will introduce let us say the some other contamination of the tungsten carbide peaks are coming here. So, this is tungsten carbide peak here. Whereas, if I use stainless steel, then I do not get this 100 reflection, that is the superlattice reflection of nickel aluminide, but in case of tungsten carbide I am getting this peak actually. So, I have reached to a process where I can produce some ordered structure. So, optimization of the milling media time, so they play a strong role. So, the synthesis of nickel aluminum using nickel aluminum blend using a stainless steel media that causes some iron contamination in order let us say of the range of 18 atomic percent. However, using a hardened steel or let us say the chrome steel milling media having a better wear resistance than the stainless steel. So, the contamination level is 5% only. So, we can simply bring down the contamination level from 18 to 5%. So, the extent of the contamination depends on the milling media, milling speed, the type of mill, whether it is a high energy mill, vibratory mill, and so the advice here that the powder and milling media should be in the same material, but this is impossible. Let us say if I want to mill a nickel aluminum, then I have to create a vial of nickel aluminum, and that is not really possible, but at least we should choose the hardness level in such a scale, or let us say if I want to produce some zirconium oxide, then zirconium oxide vials are possible to make. So, that kind of consideration has to be taken for using any of these non-equilibrium processes, or let us say the top down process such as mechanical alloying. With this we finish our discussion today. We will continue with different other non-equilibrium and equilibrium advanced processes in the next class. Thank you.